every column or feature that you're going to apply normalization on, your data in that column is going to be in a range of 0 and 1. That is minimax scaling or normalization. It's going to do a uniform scale of 0 and 1. So let's say you have a column of let's say age, the normalization bit or min-max scaling is going to provide. There's some formula we use. I don't know if I quoted it. I don't think I did. But that after using that formula, I think it's that value minus the minimum value over the range of maximum value minus minimum value. That is the formula for min-max scaling. So after applying that formula to all the values in your column, all your values are going to be in a range of 0 and 1. And we usually use minimax scaling or normalization when the algorithm requires data that is in a bounded interval. So when you do minimax scaling, your data will be in a bounded interval of 0 and 1. Then the other bit of feature scaling that you can use in case you don't want to limit your data, to bound your data in an interval of 0 and 1, is called standardization or the Z-score normalization. So what this does, it makes your mean, the mean of your data. Let's say you're working with one column, it's going to make the mean of that data 0 and the standard deviation to be 1. It also has a formula. I don't know why I didn't quote the formula, but if I remember correctly, the formula is that value, let's say x, minus the mean over standard deviation. That's the formula we use for Z-score normalization. And I think most of us came across Z-score normalization when we're trying to detect outliers. Because if you have data that has outliers, a column that has outliers in your data, when you do this standardization, it's going to make sure that that data follows a given pattern. That data is uniform using that formula. Yeah. So what all you need to know is if you want your data to be bound with the bounded interval, then you can use the minimax scaling, which gives your data a range of 0 to 1. Or if your data is free and when the algorithm you're going to uses, it assumes a normal distribution. You know, the normal distribution curves we used to do, when the middle part is the mean, and then these other sides, there are the deviations. Then you probably do the standardization in your data to prepare it for machine learning models. So for me, since our data, the columns, they were not bounded, because we had some columns where we had 1s and 0s, and then others are 200s and 300s. I didn't use minimax scaling, I chose standardization. So this next bit, I applying standardization to our data frame. So to do standardization, there are some things we need to import, and you first need to install sklearn. So standardization, so since standardization is like all feature scaling is preparing your data for machine learning models. One thing that I realize that most machine learning models expect your data to be in numerical format and not in categorical format. So as we're doing standardization, we are standardizing the columns that are numerical, and then we're doing what we call one-hot encoding to the features that are categorical. Standardization, I've explained that. Then one-hot encoding is like getting the categorical data and changing it into binary data of of ones and zeros. So in the main process, you're turning categorical data to numerical data because machine learning algorithms do not use non-numerical data. So an example of one hot encoding is like when we have a column of sex, and then in that column, it has females, males, females, males, in when it is categorical. So what one hot encoding will do, it will get the column of the sex and then create two other columns, one for sex female and then the other for sex male. If you get a row where that person is a female, the sex female in the sex female column, there will be a 1, and then in the male will be a 0. Then when you go to male, there will be a 1 in the sex male column and then a 0 in the sex female column, like that. So it will either be a 1 or a 0 on each row. And this other column that is one hot encoded will probably be eliminated because that data is now described or represented very well in the other two columns. So in applying standardization to this frame, after importing the libraries that you're going to use, the categorical features are 6. So on our data set, I realized that most of them, the columns, even though all the columns have like numerical values, right? They have 1, zeros, some have 3, but not all of them are numerical. Because it's like when you're doing feature engineering, you have to study the data you're working with and know if it is categorical or numerical. Like for example, if I do this CP, it has values. Okay, let me first try to see.
Background is not favoring for today, eh?
Background.
Yeah, there are a lot of people talking in the background. I don't know whether it is you or someone else. Are you on campus?
Yeah.
Okay.
Let me try to.
No, you proceed.
I
So
proceed.
just ignore.
Okay, so when like I was saying, this CP is like just pain type. So if you look at the data set we had, the heart data set, this just pain, there are these values, they have 3, 1, 0, and all that. But you might see that these are like just pain types, and they're like maybe you have type 1, type 2, type 3, type 4, not necessarily saying that a 3 means it's a numerical value, it's just representing a category, a kinds of types, yeah? So that's why most of these categorical features, these columns are in the categorical features. Even six, you have 1 and 0, but you might realize that the 1 is for males and then the zeros is for females, yeah? So if the males is for males and then the 0 is for females, so that's why it is in this category. Then for numerical features, that's why we have age. These are like the legit numerical features. So on this side right here, I provided a transformer to transform the data. So sorry, I was trying to find some other place. So here we transform the data. The one that is categorical is one hot coded. So there will be different columns that will be created. And then this one, that the numerical features are going to be standardized. So yeah, they'll have a mean of 0 and uh, a standard deviation of 1. So this one, for the numerical values, we apply the standard scalar because we are standardizing them. But then for the categorical values, we provide the one hot encoder because you're just providing, we're just getting other values, other columns where the where which are binary, like I explained using a 6 column. And then after this, we need to transform all of this. Remember, this was in our data frame. So we need to transform all this into a data set. So,
Elsa, you just move faster a little bit because I want one more person to move through.
okay.
Just like I said earlier, the goal is not to understand the code one by one. The goal is make sure to understand what we should do when dealing with the machine learning problem. Because right now, our focus is going to be mainly to look at the modules, building the modules. This is good for giving out like work that is well represented. But for understanding purposes, our goal is make sure that we look at the flow of how we are going to do the pre-process. Basically, that's the steps. Yeah, the understanding of the code that will come when I will be firing questions. For now, your goal is to understand how to do the work in a logical, in those steps from start up to the end. And I think, yeah, using one encoder, all those steps are okay. Just proceed so that at least we can have the first 1 hour. We have about 2 people presenting. Then from there, we will try to move, show people what they should do. Then all this one can be done because you cannot do the work in the same way. You can handle the work, the same data set, you can handle it in a different way. So try to move a little bit faster.
Okay, so this is what the data frame, the new process data set we are going to use for data split, for prediction is going to look like. You divide you just make everything numerical. Then now on to data splitting. Data splitting is like you're getting different subsets, one subset for training the model, and then the other one is to test the model. So I imported train test split to help you split the data set. So before splitting it, you need to divide the ones that are these variables that has all features except the target column. You put them in one set of its own, then the target on its own. Then after you divide it, you divide the test, you divide the X, the all features, you get the train, you add some to the train, to the, yeah, training set, and then the other one to the testing. You can divide it by 30/70 or 20/80. Me, I used the 30, if you see here. I use 30% for testing, and then the training, the 70%. So this was just seeing how your testing data looks like, and then your training data, and then knowing how many columns you're using for testing and training. So for me, the training set, I have 211 columns, I mean rows, and 34 columns. And for the target, only has rows and there are 211. Then testing set, I have 91 rows and 34 columns. These, these, uh, these things, this data set, dividing them into training and testing subsets is random. It's not like you get the first 50 rows and put them into the testing or training. It is done randomly. And then I try to do some machine learning models. I used supervised learning, is what I started with. Um, I started with linear regression. So I imported linear regression for the model and then mean square error for like knowing the accuracy of the model. NumPy is just, it's just that this is going to be totally numerical and NumPy may sometimes be needed, but I didn't use it. So I created the model for linear regression right there. And then I gave the model that training data, the X train and then the Y train for training. So this is basically training. And then so this was giving me an error for missing values. So this is what I was trying to do here. So make sure I don't get that error. But usually you don't have to do this because it's done in preprocessing. So making predictions is like after training the model, you need to make the prediction. So this is the prediction for my model. You predict it using the X test. Remember, we saved the 30% for testing. So it's like you give your model a test so that the X test so that it predicts the Y test now. So this is what it does. And this is like evaluating the model, testing its accuracy. That's why we get the mean squared error. You give it it's like the Y test. Remember, we were using X test to predict the Y test. So your prediction is Y prediction. You're seeing this is what your model has predicted, and this is the actual values. So the mean squared error is trying to get the relationship within this and then create and shows how much your prediction is right or wrong. Then this is just comparing my predictions and the actual values. So the mean square error is 0.13, and the less the mean square error, the more accurate your model is. So if mine is 0.13, I think it's kind of giving. If it was like 0.3, then it would be bad, but 0.1 is not a bad accuracy. And then when we try to compare, this is what my model predicted, and this is the actual output. This is 0, and this is negative 0.1, 0, negative 0.4, 0.6 has a 1, 0.2 has a 0, and 0.9 has a 1. So it's not that bad. And then remember, I told you I was trying to use this model to know which ages are more likely to suffer from heart diseases. So that's what I did here. So what basically this code does, it measures the prediction, the average predicted probability of every age group and finds them, then the one with the highest predicted probability, the age group with the highest average predicted probability is the age group with the highest possibility of getting heart diseases. So that's what this code all does. When the output at the end of it all, this is like a summary. What happened? The middle age group has the highest average predicted target. It has 0.6. So meaning, and then elder senior 0.4, then elder 0.6, and the young group has none, meaning there are no possibilities for them to have heart diseases. So the most likely group to suffer from a heart disease is age group middle aged with this predicted target. That is linear regression. I tried to do with Kennen, but I was getting some error. And that's why I stopped.
Okay, thank you so much for the presentation and showing your work. At least it reduces the overload of explaining each and every line of code. That is very wrong to students who are going to learn programming. Remember, I said it earlier that the goal is to understand how the work is done. Exactly, that's what Elsa is doing. Understand, you're not going to understand this code like one line at a time, okay? And that's what I expect most of you to do, because I have actually outlines of what you're going to do. Remember, at the end of the day, I'm expecting a conclusion, your actionable insight of the data, and then which you write the report, then you're going to write the recommendation, and then you're going to give me the conclusion. So what do you conclude from the analysis? Okay, so that's the goal. The rest of the course you master it with time, because you need about 12 years, no, 12 months, I mean, or 6 months to understand all these codes one by one. So if you're going to do a project, just understand that if I need to do normalization, I need this kind of code that helps me do that. Can you have a gentleman to present maybe like in 14, 15 minutes? Then I'll try to show you what to do. I like the way Elsa has actually started working on the problem, and that's a good one. Okay, let's have another person.
Good evening. Good morning, rather.
Good evening, good morning. You're in the evening hours already.
Are you guys seeing my screen?
Yes.
Okay, I did some bit of data splitting and cross-validation. Like last time, the teacher had talked about some selection, feature selection and scaling. So I did some data splitting here. Like we remember data splitting. The essence of it is to split your data into two tests. For example, into two groups, the training group and the testing group. Usually, is with the ratios of 70 to 30 or 80 to 20. So you import from scikit-learn, you import this function train test split. So like you're seeing here, I load the data. This X, okay, here I drop the target column of feature, and then the Y is the target feature. You split the data set with this line of code, like XY, test size is 0.2, meaning it's 20%. Like the previous speaker said, you can change it to 0.3 to make it 30%, or any of your choice, but usually the recommended values are 20 and 30%. Then this random test, the teacher talked about it on Wednesday, like it's just used to shuffle your data, as in it's used for shuffling. Here I check the split.
Reproducibility of the data. So the random size is basically for it's actually it's a seed value to ensure that the split is you can reproduce them. That means you can use the same values to produce a random split. So that's the random size.
Okay, so when I print here, that X string, the shape of the X string is 242. This first one here are the rows in the data, in your data frame. This 13 here are the columns of features of your data frame. Of the train, okay, the 80% of the rows are these ones. So let's try changing here maybe to 0.3. We'll see that number changing. You see now it's changed to 212. So these are the 80% of the rows in your data frame, and the 13 are the columns of features in your data frame. Now, this 61, I've changed it back to 0.2. This test shape, 61 is still the 20% of the rows in your data frame, and 13 are the columns of features in your data frame. Remember, the Y, our Y is only one feature. So that's why we've only listed one here. This corresponds with Y train, it corresponds with the X train. Y test corresponds with the X test. But here there is no need to include the other thing because it's only one feature or one column we're using here. Then here I didn't comment. Let me try to comment something here. Here we're doing some cross-validation. Cross-validation, okay. it helps you split the data into groups for validating the data. There are types, okay, methods that are used to for cross-validation. The first one is the k-fold. The k-fold basically splits the data into subsets. Let's say the k number of subsets. Let's say k, let's call k, like for example, 10. And then removes one data set for training for 9 data set. Let's say our number is 10, our k is 10. 9 of those 10 are going to be training folds. Okay, they are called folds. Training folds, then the remaining one will be used for testing. Now, each fold is this method makes sure that each fold is, as in trained, is used as an example of is used as a training data set, or okay, as a training fold. Even the first fold used as the testing fold. So at the end, each fold in the 10 of them, and all 10 of them are used as a training data set. So here we use the k fold. For cross-validation, you have to import this method, which is the cross-val score. Then we are going to use this model, logistic regression. This is the normal thing we did up there. Then we create a model, which is a logistic model here. We are using a logistic model here. So this max iter equals to 1,000 is like giving a limitation of iteration of your model, like for example, to 1,000. So it shouldn't exceed 1,000 for it to converge. Or is it converging? I don't know. Maybe. Specify cross-validation strategy. For example, k-fold here, k is equal to 7. We are going to create 7 folds from our data. This is the same. You create a variable, you assign it to these things. A k-fold, which is the method we are using here. Number of splits is 7, shuffle, and then random state. Score, perform cross-validation. Here we are performing cross-validation. So if you run that thing, we are getting, for example, for each fold, for example, for the first fold, 1, 2, 3, 4, 5, 6, 7. So after cross-validation of all the 7 folds, these are the performance scores for each fold. Like for the first one, for the second one, for the third one, for the fourth, up to the 7th. Now we get the mean of the scores of those 7. Remember, we are measuring the performance of our model here. So we get the mean of all those 7 folds, which is this one. Now I tried to use the stratified k-fold. Still, you import the same method of cross-validation, but here instead of k-fold, you specify to stratified k-fold. Stratified k-fold, the major difference between stratified k-fold and k-fold is that when k-fold, remember we're splitting data. When k-fold is splitting, it doesn't care much about the specification of classes in this data. But for stratified k, when splitting this data into folds, it makes sure that it groups these folds, okay, the data in these folds with similar class features. For example, let me phrase it like that. So here we scale the data. This one was taught by the teacher last time. Now, still we are going to use logistic regression as our model. Now, max iter, this, we saw it in the first thing. This solver, okay, it's like the algorithm we are going to use for this iteration, liblinear. Specify the cross validation. For example, stratified stratified K fold with K equals to A. No, here I used K equals to 5. Now, the number of splits is 5 here. The same thing that like we did there. Now we get the scores for each fold. 1, 2, 3, 4, 5. Why is it 7? Let me rerun the code and see. 1, 2, 3, 4. Hmm? 1, 2, 3. Excuse me, teacher. I'm requesting maybe if you've seen something wrong with this, that why is it printing 7 instead of 5 folds? Excuse me? Because I tried to.
Hello? Yes.
Yes.
What do you say?
I was like, I'm trying to use 5 folds here in the stratified K fold, but the cross validation scores are bringing 7
Maybe you
7
need to
folds.
run all you need to run all the cells.
I need to run all the cells. Still the same. Maybe. No, the problem is here. Yes, that's it. The problem was there. So it brings the scores of all the 5 folds we've created. 1, 2, 3, 4, 5, and then it calculates the mean of all the 5 things. So that's what I was able to do.
Thank you so much. I think most of you did now reach the modules. You did reach the matrices for the predictions. Is there anyone who reached up to the matrices of using precision recall and then was able to get some of the module predictions? Anyone who has reached up to that point? Or no, and then I take over from there. Okay. So let me just take over from there. Okay. First, I want to appreciate those ones who have presented right now. You people did a great task over the weekend. No, over I think Tuesday, no Thursday. You did a good job. Now, yes, I have.
I have for the models training and selecting a model.
You worked on one?
Selecting models and how we can come up with the model scores to see which model best fits for our data, for whatever we want to query.
Sure. Shall we proceed?
So I hope everyone is able to see my screen. So other things have been talked about, so I'll just rush through. So my machine learning was structured in this way, in that I first do some correlation to know which variables are going to be dependent and which ones are not going to be dependent. Then when I'm done, I do some encoding, whereby, remember, in machine learning, we are only dealing with values. So we wouldn't have to have columns or data sets which have alphabets or something, which is other than which is a number. Okay, so that's why we do that encoding. Then afterwards, we can now start setting and training our data sets. Then from there, we can do model selection, which models best fits, then we train it. Yeah. So if someone can recall from the last lecture, some 2 lectures back, this is what Mr. Jeff was trying to do. All this code was all about how can we convert our data. For example, this categorical data, whereby we had rice, other rice, potato, something. So here I was just trying to convert that text data into codes, into values, numerical value. And this one has been talked about by Elsa in code encoding. That is if we are using standardization or normalization. So we have all seen correlation. So amongst my first steps, I first did some correlation to know which ones are dependent, which ones are independent. So which we have been going through for some other time. Then from there, I did some encoding. Now in this case, for me, I used label encoder. Label encoder converts grouped data, whereby you have a column, and that column has repeated values, which are not numbers in terms, but text. For example, in the labels data, let me share with you this data set. You can see I use the crop data set. So if you can see the crop data set, labels here, we have rice, maize. So this is categorical data. In other words, you can group it and assign them values. So here I used a label encoder and import it from that. It's a class, so I create its object and assign it to this variable. So I can access now all methods in that object. For example, the first method is fit transform. Fit transform, what it does is that it gets the other non-numerical values, converts them into numerical values, and then afterwards I'm reassigning them to my column labels. So if I print labels, this is what you see. Instead of having rice, now rice is going to be represented in terms of 20. And let me first give you a visualization of what I'm trying to talk about exactly. If we had come up here before even, okay, let me write it something. If I print EF label like this, you can run. Let me put here. And then don't know why it's taking long. And there's something I wanted to show, but I don't know why it's not running. Because of time, let's first go back and continue. So what here I'm trying to mean is that here label has been changed. The first 5 records had rice. So instead of having rice, we are having rice represented in terms of numbers. This comes up because label had very many elements in it. So each element is going to be assigned a value instead of using its text name. So that's what I had. Then after, when I'm done transforming, now I'm sure now all my data has been converted into numerical data. Even that data that was in text form has been converted into numerical data. Now I can proceed and do data training and data setting. Now here, as everyone has said it, you can train your data. You divide training data and is all about you split the data. After splitting the data, for example, here I can split the data. That training data will have 70%. Then of that remaining data, which is 30%, will go for test data. Now, when you train the data set, we are going to have Y and X trains. Like we shall have out of this 70%, Y will have its 70% as a training data, and X will have its 70% as the training data. However, the other 30% remains as Y, and the other 30% also remains as X. Okay, so training data, this is what we do. Line of code, we import this class, okay, a module which we're calling a module. Then from there, this is what we have to do in this order, and also provide this in this order. What happens is that when I pass in this X is going to be divided into two, into training data and the testing data. Now, when X is divided, the 70% of X goes to training data, the 30% of X goes to training data, okay? Same thing happens for Y. Y will be divided into two, 70 and 30. The 70 goes to training, the 30 goes to testing. The size will all move. That's the random state, as Mr. Jeff said. After splitting this data, you get some numerical values. So when you get this, in other words, you can convert, it helps you to convert back your data to the original, like you're combining it. Okay, so here when I print the training data, these are some of the records we can see, and we are saying we shall get these records. Okay, so that is all about training. So when I'm done training data, I do some bit of scaling. Now scaling is all about convert a very large number into a small value that the machine can easily iterate through during its operations. Here we don't want to see machines that are operating or working but very slow. Reason being, they are trying to make queries on very large values. You know, if a number is next to each other, you can easily work with that value, other than working with values whereby you find one value is like 100, the other value is like 10,000. So if I'm searching for a value, finding that case, it becomes very hard. The machine will have to always iterate, go to bigger values, come back to the small. So you find that the machine slows down. So we want to work with values in a given range. So that's what we do with scaling. Now in this scaling, we have two categories, as Naja said: standardization and normalization, depending on which one you want, because each one has a point of application. Okay. Now in this case, for me, I worked with normalization. You know, normalization is bringing a value to a given range. Okay. This is what happens in the background when we use normalization, but it is implemented by default. Just was a bit of what normalization is. Now, for that case, I use a minimum scalar. Now, minimum scalar is what implements normalization. And in this minimum scalar, by default, it will scale your data between 0 and 1. Okay? But you can also override it and say, you tell it, I want you to scale my data between maybe 0 and 10. Okay, so it means it will convert all values which are, let's say, 10,800, blah blah, in terms between 0 and between 1 and 10. Okay, that's what it can do. So to implement this, we just say future, then you provide the range. So in this case, I want between 1 and 10. Okay. Okay. However, because of time, we would have shown you everything and how they are. Okay, we can try out anyway. Now, for example, here. Now, the other thing I forgot to talk about is that when scaling data, we most times scale the X testing and training data because X always represents the data that we are using to predict Y, okay? And in this case, Y becomes the dependent variable, in that for you to know Y, you have to use X. So X becomes the one we are going to use to find out Y, okay? So in that case, we are working with X data to predict Y. That's why you find that most times we do scaling on the X train and X test data. But it doesn't mean that Y data can't be scaled. It can also be scaled. But for it, it is quite a different way because it's quite a different way, though it's not that hard. So now here, I want to demonstrate to you about this future range. Now, here when I scale my training data, I'm going to store it here. So let me try printing this to the screen. So when I try to see the training data, you see that this training data, it is, for example, this first record, all values are either will be between 0 and 1, okay? But I could say that I scale my data between, let's say, between 1 and 10. Okay, run this again. So you can see that the data changes. Now, for example, in this record, the data will be between 1 and 10. So you can see we have 2.8, we have 9, you know. So that is what happens with future scaling. You're trying to convert your data into a given range of value that is easy to work with, okay? Now, when you're done with the scaling, you are now sure that your data is within a given range and it is now easier to use with, and our machines won't be slow. Now you can come and you select which machine learning model will be best suited for you. Now, to do that is very easy and it will work out for almost all the machine learning models. What you have just to know, when I want to use this model, where am I going to get the model? From which, how do I access that model? Okay. So here we are using the sklearn library, and we have to target that specific model that we want, and afterwards you import its class. Okay. So from here, I will just explain this, then the rest will be the same things. Now from here, as you can see, I imported this class. Now this class, I call it constructor. For those who know the things, I assign it to that. So the reason as to why I'm having this line is because I want to access methods from this class. So when I assign this here, now I'm able to access all methods that are in the linear regression. For example, if I say log reg dot, so here, these are all those possible methods that I can get from this class, okay? Okay, we continue. So from there, what you do is, remember you're training a model. So we are going to deal with training data, okay? So you provide the X training data, which has been scaled, and the Y training data. So since we are training, we're only dealing with training data. So this fit method will fit that data into this model, the linear regression model, okay? So when we train, for those who know machine learning, this is a supervised kind of training whereby you provide it with input and you are aware, you also provide it with the expected output. So this is what we're trying to do. Provide it with the input, provide it with the expected output. So every time you're testing, it will be relating to the expected output, what you expect, okay? That is the supervised learning. So when you are done training, now here you can do the testing, the predictions. Now in this case, you will have to use the training data. Since here we are able to access all the methods from this class through the dot notation, we are going to access this method, which is predict. So this predict will help us to know what will be the output for y. So what it does, it relates, you have given the test data, which is the input. So it relates it with what we expect from y. Remember, this was the expectations that you provided it with, okay? So from here, when I print what I expect, this is what it gives me, okay? Now from there are other methods you can access, for example, the score, the mean score. And this one will help us to get the mean accuracy score, that how accurate is this model, okay? So this is what we get. So for the first line, when I run, we get these values. Then when I try to run this, sorry, this one here, you find that we are getting the mean accuracy score as 0.3 plus other values. So you will do the same thing for other models. Same thing for the decision tree, that, train it, predict, and also you can get its score. So for it, it gives us 0.9. Same thing for the random score. Just need to know from the library way of importing it, which class is supposed to be imported. These other fit methods remain the same. So for this one, it will give us this. So you see that when I
please, what do you want to say? Because I want to take over and summarize this stuff.
okay,
Yes,
so everything remains.
thank you. My argument is just more about on the use of. Are you hearing me, guys?
Yes.
Yeah, we are hearing.
Yeah, about Derek. Derek was trying to fit the transformers using the fit transform method. I think if you try to scroll up again, when you use the fit transform method and you on the test on the
Where
train
exactly?
up, yes, there.
Here.
You see where you have X train scaled, and you apply this fit transform on the X train data set. Yeah? And again, you apply the fit transform on the test scale. Here, you're going to produce data leakages. Do you understand what I'm saying? The fit
No.
transform method on the train scaled, it's only applied on the train scaled, right? It's used on the training data. It basically performs operations like computing the mean and standard deviation for scaling from the training data. Then the transform applies the computed statistics to transform the training data. Understand? So you have to,
Okay.
you shouldn't use again the fit transform on the test data, on the test scaled. You just have to apply the transform method, not the fit transform, such that you don't produce, it uses the same statistics from the X-trained scaled. You understand? So why the
When
difference?
when you look at this here, we have fit trans.
Yeah.
Yes, and
Instead of using.
Okay, what I want to summarize from there, allow me take over. Derek, could you scroll down and
yes,
I see if you were able to do the recall.
no recall I had not yet.
Okay.
But
Thank you
I
for
think
presenting. No, it's okay. Thank you for presenting. I want to take over. That was Seron George. Please, I'm going to take over and I'll explain that so that we save a bit of time. Because, but thank you everyone for presenting. The advantage of allowing you present is to avoid the other the other group complaining that, oh, what is the test? You're not understanding. No, just to give you and see. We had about 3 presenters. They had totally different codes. So you're not going to understand because the code that works here may not be the one that depends on how you are doing your future engineering. But allow me a little bit move faster so that I can at least give you a picture, because if you are able to see from me, then you're going to be able to understand my expectation. Allow me start a little bit slowly to help the other group understand. The one who want to understand line by line of the code, then I'm going to speed up, boom, up to the end so that we don't need to waste a lot of time. Now, the other group, allow me just for that particular group, that's my interest, just for about 1 or 2 minutes. Now, the other group of students is that when you're talking about data, just allow me move through it. I'm moving faster. My aim is different. When you look at this is how I expect you to do your work. Conclusion, all this, I have a way my expectations are, but I'll talk about it when we come on campus. But the main thing right now is first to understand a little bit, how do I do splitting? How do I do, basically, my goal is for you to understand, first know how this is done. Then you will go back into understanding the code. Because now I need something in matrices. How do you do module evaluation? How do you get regression? These are the things I'm interested in, okay? And since I'm interested in all, I think up to here. We are not going to answer by. So up to here, repeater over receiver operating, receiver characteristic curve, receiver operating characteristic curve. I'm interested in all these regressions, K-model, decision trees. So please mute. I don't want to hear any noise from that end.
Excuse me,
Okay.
sir.
Yes.
I'm requesting for you to increase a bit on your font size, sir.
Okay. That's understandable. Is that better?
Yes, sir, that's
Okay.
better.
Is that better? Okay. So my whole goal is for you to know the flow. I'll later come to campus and try to show you my expectations, what I need you to follow, how do you deal with outliers, categorical. I have a way, how do you transform your data to skill, all the things we will be physically trying to help you. But right now, since we are learning, you cannot learn everything. Let us accept that, okay? All right, now, let me come to libraries. Now, sometimes when you're working with the machine learning problem, you're quite aware that if you have this kind of outflow, like steps that you're going to follow, sometimes it is better you import all your libraries at once. Pandas, NumPy, all this. Now you see you have even from module selections, training and splitting, stratified fault, cross-validation score. You just import at once. And then the select K-based for future selection, all this, the module for the K-nearest neighbor, linear regression and logistic regression, you import them at once. Support vector classifier for SVM, support vector machine, decision tree. You can import all these libraries at once. Then you also need to import the library for accuracy score, precision score, recall, F1, confusion matrix, ROC and OC score, and then ROC curve. you need to import all these modules at once, sometimes, so that you save yourself. Then you need to import matplotlib because you're going to have some repeater operating curve, then sequence, so that now you don't spend a lot of time. Then you read the data set. Basically here, what you do with the drop is that you want to drop the target data because it's not the data that you're going to use for X-train and X-test. Okay, so then you go to feature engineering of the data. You can pick columns that you want to play with. I've just tried to go general. Then when it comes to X predict, of course, you need to drop the target column, then you only remain with other 10 columns that you will be using it for your predictions. Now, when it comes to splitting the data, which everyone up to this point has understood, but the other group of students, what they wanted so much is that when you write a line of code like this, you need to tell us, what does X-train do? And then you need to tell them that this is what the X-train is basically for training set features of your data. Then what does X-test mean? That is the other group. This is for testing set of the data that you have kept. Now they need also to understand, what does Y-train means? They want to understand that the Y-train is basically training set of the label data. Now, what about the Y-test? Testing set of label data. Now, because we imported this library that does the splitting, so you're going to split them because you're going to make predictions. And you need the actual data and then the predicted data. That's why you try to split the data into the actual, and then the predicted one. Now, the test size of the data, those group of students want to know, but it's your duty to specify that the data that you're going to use for testing is going to be 20% of your entire data, which your colleagues were able to show you. The remaining 80% of the data is going to be used for training your module. Then what does the random state means? Why are you using 42? 42 is basically, you will split the data so that if you need to revert back the data, reproduce them. So, because you will use the same data always, and then you can also produce the same random split with your data. That's why you use the random set of 42. Now, that is that particular group of people. Then when you're done with that line of code, the moment you're going to write another line of code, that group needs you to explain, okay? They need you to explain now the next line of code. Why are you writing that line of code? And that is the kind of group that you're going to be working with. And it's kind of funny because now, if you're going to split your data, which you've done the splitting of the data, I'm just trying to make sure that I am a little bit okay with also that kind of group of people. Then we can now start moving forward. Now, like me, after splitting my data, I don't know whether I've done cross-validation. If I've not done cross-validation, because I've just started, okay, I've not done cross-validation because I am always trying to make sure that I follow this kind of procedures. Okay, so the next part is to, basically, you're doing cross-validation to evaluate the performance of the data with multiple faults. Now, I'm going to make it a little bit general, okay? So that I can have the stratified k-fault to make sure that I can evaluate the performance of the module. So what I'm going to do here, I'm going to write cross validation. Now, please, then that group of people are going to be asking you, what exactly are you doing in cross-validation? They need you to, even before you write the line of code. But what did I say about that? Cross-validation is basically to evaluate the performance of the data. That is it. If you understand that it's used for evaluation of the performance of the data, what cross-validation are you going to use? Okay? You can use stratified k-fold, ensure distributions of the target data, and then also dealing with what we call imbalanced data set. Because sometimes, based on the kind of the data we have, you can try to look at the cross-validation scores, and then it will help you understand the kind of data you have. So you need to write that code that does the cross-validation. So in most cases, if you're working with the same kind of data that you're familiar with, now it is easier for you to just go ahead and do the cross-validation. As long as, if you're running, as long as you have already imported the module here for doing the cross-validation, which is here. Scikit-learn, then import, stratified, and cross-validation. There's a mathematical formula that will do that for you. It will take care of that, so you don't need to go and cram the maths. So now here you just go ahead and make it in the easier way and say you could create a variable, and then now this is where some of you get annoyed, because whenever I said your goal is to do the cross-validation. Next time you will try to understand what does this line of code do. So you can also use what we call the random forest classifier. If you go back to my previous part, is that okay, there are several ways how you could do it. So I don't need to trick your mind into, you could try to explore. You don't need to cram what I'm doing. You just need to understand. So now you could use the method for random forest classifier. It's having some formula that will take care of the entire data. Okay? So now for me, even to save time, I'll also try as much as possible to just explain to you that now here I'm trying to use the random forest classifier module basically to initialize the random forest classifier. Then I'm going to, because I'm using the word cross-validation, I could also write the entire word and say cross-validation. So I've created a variable CV, which is cross-validation, that is setting up a stratified k-fold. Now, in the stratified k-fold, to make sure that I ensure the target variable distribution is maintained across all the folds, like the splits are 5, just like the way someone was trying to explain that you can create the folds into different numbers. And then after doing that, then I'm also trying to perform cross-validation on the training data. That's why I'm trying to do what we call trying to see the performance of the cross-validation, the performance of cross-validation on the training data. That's why I've created another variable for score, so that if I'm able to get the cross-validation score and the mean of the cross-validation score, it will help me now understand my performance of the data. So if I want to get an output of that, I can just do a print for cross-validation. Okay. And then I can also do print also the what? I could also print let me have it as a formatted string for the mean. mean of the cross validation. Okay. Now, if I run this and I get an error, maybe it's because of suggested, but I could go ahead and what? And rewrite that code. So that's why sometimes you have what you want to do, but the way you implement it also does. So now here I could try to, okay, I'll just try to improve. So I will have it take, I'll pass in the parameter module, then because I'm trying to validate the scores of my actual and then the predicted. Then since I could try to modify this and basically to avoid I hope this time I won't run into stratified default. And still it's not defined. Why? Yes. Not defined. Okay, let me just rewrite all this. This one. Okay. So what basically sometimes you could allow that suggestion of the code, but what you're interested in is to look at the performance. So when you look at the performance here, basically, just like I said it earlier, our cross validation is having an accuracy of 0.8. Okay. Now that means 0.8 is like 82, it's like 80%. 80% may not be a very bad performance. Okay. Now, once you've done the cross validation, remember this line of code is basically just helping you to determine the performance of cross validations on the training data. That's why this score, which is printed alongside the mean, is basically to help you. It's basically to help you understand the performance of your data. Then we are now going to the next part, which is going to be training. Okay, when you do the cross validation, it also helps in reducing the variance in the module performance estimate. But for now, this is what we will use. I told you don't mind, but just understand why you're trying to use that. Then we proceed. Now, let's first go to the other part of it, of doing what we call the module. You're trying to do what we call training and evaluating. evaluating the module. Now, for training and evaluating the module, your main goal here is that you're going to have the training data to evaluate the performance of the test data. Is that okay? So your main goal is to, because if you understand your main goal, the rest of the code will do it. Your main goal is to have the training. Your main goal is basically train the module on the training data. So you're going to train the module on the training data and evaluate the performance of your data. Then, if you want to go ahead, you can print the test scores of evaluations of your module. So, so you're going to basically do some bit of fitting. So you're using random. Okay, there. Let me just try to use the tab. Then I will explain this. So this is what you are predicting, and basically what you are interested in is you want to evaluate the scores of your test data. So you could also do a print. So you could also print the accuracy. Now, when you run this, it is giving me an accuracy. So this accuracy is basically the test score accuracy of our data. Now, when you look at this, basically trying to see your prediction, you try to look at the accuracy is 85. Our cross-validation is 82, but our accuracy is 5. That means you're now going to be a little bit confident that your module is going to perform well because of the training and evaluation of this module. Now, because you were able to clearly train the module on the training data and evaluate its performance on the test data. Now, that is where now it's going to be interesting for you. Since you already have some bit of the test accuracy, this is just to test and see whether your model will perform well. There's nothing much. This is just a test score accuracy of all your modules. So you're going to have it at the mind that most of my module will perform between 0.8 and above. If I get a module that has a performance of 0.6, that's where now you start getting worried from that your module is not going to perform very well. But the reason why I'm doing this, I have only one goal, which we are going to fix it. Now, let's first look at that. Now, we've done cross-validation. We were able to do some bit of evaluations of, we've been able to look at some evaluations of module performance. Now, let's try to get some of the algorithms. Let's go here. Let's try to get at least some of the algorithms, which we are going to be interested in. We are going to first look at the logistic regression, the k-nearest neighbor support vector. We also want to look at the accuracy of those modules. Now, as a machine learning expert, of all these classification problems of all these modules, which module can I go ahead and deploy? You have all these modules, but you're going to deploy all these modules based on the performance and accuracy of the module. So now, then once you do that, then you will be able to go to the matrices, then you will be able to do the confusion curve and the receiver of priority curve. So, but let's first look at each performance of each module, the logistic regression, KNNN, support vector, decision tree, and the random forest. Let's look at the performance of all these modules. Now, the lazy way I would have been to write here. Basically, you're going to look at the classification accuracy of the algorithm of the all right. So now, since we yeah, it's actually trying even to get for me import precision. Yeah, we can import this. This one has nothing, but we already imported it. So we are interested in looking at that. I'm going to try to write, I don't want to recall the precision. Yeah, we could look at that. But I want to write the code in a different way. I want to write the code in a way that I can have a graph that represents that. So I'm going to ignore that unless my code start failing to work, then maybe I'll try to use those AI generated things. I want to change my ways of doing things. I want to look at the accuracy of all those modules. So how am I going to do that? So first, I'm going to initialize all the modules. I'm going to do it in a different way. I don't want to look at each of them one by one, like the way we are doing it. So I'm going to try to use a dictionary so that I can get all the accuracy at once. Just follow what I'm going to do, and then later you would see the kind of, so I'm going to initialize the modules. Now, I know this thing is going to be very funny here. Okay, perfect. That's what I want to do. I'm going to accept this because I wanted to initialize all these modules. So I've created basically a dictionary where I'm initializing the regression module, the logistic regression, decision tree, support vector machine, the KNN. Okay. Now, that one I am happy. But now on the logistic regression, I need to have the maximum iteration. Okay. So I'm going to pass an argument here where I'll say max underscore iter. Then how many times do I want it to iterate? I can do 1,000, 10,000. I also saw someone doing it, which is a good thing. For now, I let it iterate like 10,000 times. Then the random state is basically have the reproducibility. So I can also have the random state of 42. Okay. Now, then for the support vector machine, I'm going to try to also get some bit of the probability. Because I'm making a prediction, so the probability can be true or false. But let me first get some probability. Let me first pass an argument here for probability to be true and the random state to be 42. That's all I wanted. Okay. Okay. Then for the decision tree, I can just have the random state to be 42. And then the random forest classifier can also pass in. Random set can be 42. Okay. Then how about for the KNN, the K nearest neighbor? Okay. For now, I will first not pass in an argument in this matter. Now,
Excuse me, sir.
yes.
I'm asking, why is it that for random state we always pass? Oh, okay, most cases we pass for the two.
Why for random state we normally pass for the two? Because we want it to reproduce the same data. That's what I was trying to tell you the other time. Because when you pass the random state of 42, the advantage is that many times it will first of all it will ensure that the value that you are splitting is you can reproduce it, or you can use the same value that will produce the same random split. That's why we use 42. But you could also use one or, but I think the advantage of using 42 is that it will always produce the same random split. Is that okay? Remember,
Yes,
it
sir,
was
it's okay.
randomly. Yeah, so that's why I always we try as much as possible to use the random split over or 42. In that way, you save yourself a bunch of, you save yourself a bunch of time and so on. Now, since we have done the initializing of these modules, I hope even when we run, we don't expect to have any error. Okay. Now, we can also still use a dictionary so that we can also try to store evaluations of our metrics. Now, since I'm interested here in also the matrices, which are the accuracy, precision, recall, and F1. For now, you're going to look at what I'm doing, but you expect me to be very clear when giving my key insights, my conclusions, and my recommendations of which module I can use to deploy. Now, so I can still also go ahead and try my best and also try to initialize the matrices. But this time round, I will make sure that they store empty list. Is that okay? So let me just evaluate the metrics. Now, when we talk about the metrics that we are going to use, you can just create a variable metrics. Let's see, how many metrics do you have? We have 1, 2, 3, 4. Since I'm initializing, I'm not going to, okay, this would basically give me the accuracy score. It will give me the precision score. Okay, that's okay. I could also go ahead and add in area under the curve. Yeah, so that I get the area under the curve scores. Now, this is after initializing. Now I'm going to go ahead and do what we call training and evaluating the module, where we will do a little bit of logic, and then we'll see what to do. Now, let's now train the module train and evaluate each module. Now, the reason why I'm commenting so that you understand what we are doing. So here our goal is to train and evaluate each module. So for module in modules, then you first try to fit the modules, then you can use Y. Okay, this has nothing. Okay, this is basically using your knowledge of for loop. For module name, because we want to look at all the modules. For module name, we're going to do some bit of prediction, okay? And then we're going to try to look at also the probability of our test data, okay? So for module, what you're passing here, we're fitting basically our data so that all those data can be transformed. Now, let's go ahead and try to make a predictions, create a variable that makes a predictions. So, okay, we could do a prediction for our test data set. Remember what I said is that earlier on, the X test is basically for testing. And then the Y test is also for, there's what we call the actual and the predicted data, okay? So the X test is going to be the predicted data. Then the Y test is the actual data, okay? So that's what we're going to focus on. We can also try to do it on, you could also try to do and print the module name, but I want to do it for the entire data. So I'll also try to do a probability. So I'm also trying to do the probability of the test of the data so that I can also try to look at the probability outcome of that data in the range of 0 to 1, okay? Now, if we have anything that we may need to improve, we can still come back and modify the score. Is that okay? So let's try to calculate calculate the matrix so that we can get the score. So let's calculate matrix. So right now, when you're talking about calculations of the matrix, we are talking about the accuracy, precision, recall, the F1 score, and even the area under the curve. So, okay. So for matrix name, okay, we could use this function. Don't mind, because I always say the codes are always written. Just make good use of them. As long as you don't run into error, and as long as you can understand the score of your matrix. So, okay, that's okay. Now, if I try to run this, let's see the results. Okay, perfect. So if I try to run this curve, the false positive rate and the true positive rate of our curve. When you look at the logistic regression accuracy is 0.88. The logistic regression of the precision is 0.89, which is the same thing that you need to ask yourself. Of all this accuracy, which logistic regression accuracy is better for the matrices? Which one is better that you can try to use for the matrices according to that output?
The recall.
So you realize that the recall matrix is actually better. That means it's trying to show you the predictions of people with the heart disease. We will later come into the heart diseases, but first we first need to look at the matrices alone. Okay? Now, there's something that I also want to explain to you briefly so that you understand when you are talking about the true positive and then the basing on this data. Let me just try to explain to you this receiver operating curve, the way you're seeing it. I am going to try to explain to you what the true positive rate and the false positive rate. Remember when we were trying to say, let's do some bit of calculations of the matrix here. Now, what basically, there's a formula which is being used for calculating the true positive rate, the true positive rate. This formula, which is written behind that you don't see, is that you are dividing the true positive. You get the numerator is the true positive and the denominator is the true positive plus the false negative. That is when you get the true positive rate. Then for the false positive rate, now the numerator is the false positive, and then the denominator is the false positive plus the true positive. When you divide it, that's when you get. So that's why you're trying to come up with this kind of curve. Now, what the false positive means is that is the proportion of the actual negatives that are incorrectly identified as positive by the module. Then what the true positive rate means, basically here, is that is the proportion of the actual positive that are correctly identified by the module. That's why we end up having this repeater operating curve that shows you the performance of this module. Now, in the second one, you could see the curve for the decision tree. The first curve is for the logistic regression. The second curve is for this decision tree, still using the true positive rate and the false positive rate curve. For the decision tree, you could also see the scores, especially using the random forest. So all these scores are trying to show you the true positive rate of our accuracy. Now, when you go to the raw curve of the true positive rate for the random forest, now you could also see. Now, your conclusion is basically to look at all the scores. I think this one is not performing well, based on the accuracy that you're trying to see here. So when 0.6, 0.7 recall, so you can try to do your analysis. And then, and so on, up to the support vector machine. So this curves, basically, interpretation means that it is helping you to understand how the module can detect the positive instances. That means that our true positive means of our module can be identified by these cases. Now, let us go back and understand this. We will get it. We will get it. Okay, maybe if I'm to derive a conclusion here for you, based on the summary of this curve, is that you could look at it under the logistic regression. Which matrix is performing very well under the logistic regression? Then you see 0.75, 0.8 precision. So the metric precision under the logistic regressions, rock or area under the rock curve, it's the one that is performing very well. So if I'm to pick a module that I want to deploy, I am going to analyze all this one by one and then see, okay, maybe because of how these modules were performing, about for the recall, I can try to maybe look at the recall for all. I can look at the recall for KNNA. Then I look at the recall for random forest. Then I can look at the recall for decision tree. Then I look at the recall of logistic regression, which is 0.90. Now, if I want to make recommendations that of all these modules, if you want to deploy, based on this data, we should go ahead and deploy the logistic regression module. Because the logistic regression module has a recall of 0.90. That is one thing that you could clearly tell us from this performance of this module. Are we together up to this point of looking at how you can look at the performance of this module based on the matrices? Shadia, your mic is on. Do you want to say something? Yes, you could say something. Hello?
So for FPR,
We can't hear you. Shadia, are you talking? Shadia, are you talking? Okay. Now I'm going to give you. Okay. So now I'm going to give you the actionable insights of this data. Now, you need to give what we call the actionable insight of the models. So what you're going to say here, based on the performance of the module, don't cram this code. You could even write much better. If I sit down and write this code, then I try to show it to you, you will get totally a different one. So for me, what I want you to understand is that you need to tell us the best performer module, best performer module. So what is your best performer? So best perform module. Are you sure it is the random module, the random forest that perform best? Let's look at the random forest. Random forest. No. Okay, you could also explain to me which one performed poorly. It is not the random forest. According to what we saw using the recall, it was the what? You could still double check it again. it was recall okay. Recall it was a logistic regression. So you need to tell us your actionable insights of the model. Which model are you going to deploy? Then, when you're telling us the actionable insight, also try to explain and say that based on, you could also try to mention all. Like you could let's say the random forest. I'm going to round this. Sometimes it copies everything. Okay, I don't know if you tried it there. So what you're going to say, you need to tell us the best perform modules. So you can say, I wanted to start the best perform module. Ours was the logistic regression. Logistic regression. The precisions of, you need to tell us the precisions of the module. You can say for the best perform module, like the logistic regression, which had a recall of 0.9 something, you can say it had a precision of 0. You go and check, okay? What is the precision of, I need to, logistic. I'm just trying to teach you how to write it. It had a precision of 0.88. 0.88. Then you go and write here. You write it. It had a precision of 0.88. I'm not going to be going back and forth. And then you put, then you can say it had a recall. Then you put the recall. Maybe the recall is 0.90. You're trying to explain to us. Now, then then it had the F1 score of that. Then it had maybe the rock was that. Then after that, you need to go and tell us that the best perform module under logistic regressions. You can tell us maybe it was the recall that performed very well. Okay, yeah, maybe under the curve. Then you need to also go and tell me the balance module. Okay. So the balance module, you need also tell me about the balance module of our data. So that our module was well balanced based on the precision and recall. If you're trying to look at the balance module, when you look at balance module means they are closer. So when you look at precision is 0.88. The recall is 0.88. But the gap between the recall and the precisions is high. So you can go ahead and tell me the balance module based on the data set. It's just trying to tell you how reliable our data set is based on the precisions and recall, the balance module performance. Then you could do all this this was for logistic regression. Regression. Then you could also go and do this for KNN. KNN. You need also do it for SVM. SVM. And then you also need to do it for decision tree. And then you also need to do it for the random forest. Random forest. Now, once you are done with this, you are going to do what you call a conclusion. You're going to do a conclusion. So in the conclusion, you're going to say the logistic regression is the best performer overall with the highest score in most metrics. You're going to make simple, basically how you're going to, so you're going to say logistic regression. Logistic, basing on what you're seeing. Logistic regression. Logistic regression is the best performer module, best performer module with the highest score metrics. Then you are also going to go ahead and talk about the module that needs further fine-tuning. You can also say that module that needs further fine-tuning, like maybe the KNN. Then you could also talk about module that had better precisions. Now, you could talk about all those things. Then you could go ahead and talk about what we call recommendation now. So in the recommendation, you're going to talk about modules that should be considered for deployment. Modules considered for deployment. Which module can I deploy? And then you're also going to talk about modules for fine-tuning. Further fine-tuning. And then you're going to look at ensemble methods. Ensemble method is basically look at the performance, look at enhancing performance and robustness of the module. Okay, yeah. Then after that, you could also try to summarize it with the confusion matrix. And then you can draw that. Yeah, basically you can summarize with the confusion matrix. Yeah, those are the things I expect to see in your modules. So which module performed very well? And based on the data. Which module makes the best prediction based on your feature engineering of the data? So which people are likely going to get sick? Now the KNN has said that the elderly people in this group and this group are likely going they're going to be affected. So now I want to share with you something earlier because today is the last day. Please, kindly, when I finish today's lecture and I've uploaded the recording for this lecture, please go and follow these steps one by one. If you are going to work on a machine learning data set, these are the steps that I want you to follow. They're about up to 10 steps. We could not do all of it one by one because it takes a lot of time. Okay? Up to the conclusions. What I need in the conclusion is what I've just explained. So when you're building the module, how you do hyperparameter, go and do that. So up to this point, it's already 11:20. I want to stop this lecture here because you guys took a lot of the time. I don't want to go into messing up. I can write for you my complete code and I give it to you. And then you look at it. But it's always not good. People are going to be very lazy. They want to cram your code. That's why I don't want to do that. I want you to try and always keep writing your own code. So go and look at this, take up all these steps. Any question to this point? I want to end this lecture so that I can go to the bank.
Registration link, sir.
Okay, registration link. I can do. Let me give you the registration link. So at least you have my performance of the model. Let me get the registration link. So next week we are going to start web development with Django. Because one of the project is also to build, we'll give you the project on next week, you'll see them. Just like we said, we are giving you the basics of machine learning. The time is not enough, but if sure we get enough time, one-on-one, next week, you're going to see. And then also, in most cases, I realize that people don't write the code while you're working. They come with a written code and explain. So there are two different things. When you're writing the code and you're explaining them, they're different. There's also what we call expectation. So let's just be excited for web development using Django. Still, because of time, we won't show you everything, but we'll make sure that with all your hands you get started. But you can tag along in the collaboration in the development, so that will be better. Okay, for the machine learning, it's not difficult. You just need to follow the steps that you have given you up to the end. Okay.